Hello, welcome to session one of course or week four of Technology Fundamentals. Today covering computer vision, part one of two sessions. There are many application-centric domains or subdomains of machine learning. Another one we could think of is natural language processing, time series analysis. This one's going to be focused on computer vision. We can use the power of image-related machine learning to replace, augment, or optimize what would typically be a reserved task for a human. In this session, we will use modern deep learning networks using Keras TensorFlow, design convolutional neural networks, learn about feature extraction in convolutional layers, so understanding what the sub-architectures of the neural network are meant to do. We will briefly talk about transfer learning in the context of computer vision image analysis using CNNs. And we will utilize data augmentation in the context of images. So if we remember back on our session on feature engineering, I had a punt in there referencing a later conversation to data augmentation in the context of images. This is where we're going to see it. Not a lot of new imports today. We should recognize our Keras TensorFlow imports from late last week. One new import, image dataset from directory. I'll be using that when we go into importing entire data sets to build a computer vision pipeline. A helper function for later on in the notebook when we look at some of the subtasks of the CNN. Before we get into the neural network component of this session, I want to have us become comfortable with importing images. In Python, there's a multitude of ways to import and manipulate images from a variety of libraries. And so we'll just take a sample of some of those, starting with plugging in our Google Drive so that we're able to access files in our Google Drive from Colab. All right, so I've copied and pasted my authorization code. That should finish in a moment. And then when you finish that, you should have access now to Drive in your Colab hard drive menu on the left of your browser. So you're able to navigate to wherever you have Tech Fundamentals saved in your Google Drive. All right, so you're going to go over here. I have mine under Courses. I open Tech Fundamentals, and then Data, and then Casting Data Class Practice. I'm going to click the ellipses on this folder, copy the path, and then replace this URL with that copied URL. And incidentally, well, not incidentally, as expected, my URL is the same as it was before, but yours will be different. In particular, this will be different for you, depending on where you've saved Tech Fundamentals. All right, everything else should be fine once you've changed that, and we should be able to read in the data that I have pre-uploaded into the casting data class practice folder in Tech Fundamentals. All right, so first way to read in images will be through PyPlot. Remember, PyPlot is imported from Matplotlib. Here's the import right there. Actually, we can go ahead and just copy this here for reference. We use a method called imread, feeding in the image path. The image path is a string, right, pointing to where the image is located in a hard drive. We can print the type. So what data type is this? It's a NumPy array, all right? The shape, 300 by 300 by 3. So there's 300 by 300 pixels, And each pixel location has 3 channels, presumably red, green, blue. Could also be hue, saturation, value. Those are the 2 main ways we'll save and read image files. And then with PyPlot, we can also show the image with imshow. If I don't want my minor tick marks, my axes tick marks to show, I can do plot.axis and then feed in the string off. And so that's what I've done here. If I were to comment that out, you would see the normal tick marks that you'd see on a regular graphical plot in PyPlot. Another way we can read in images is through CV. They had a version change where they now call it CV2, so I'm importing CV2, calling the method mread again, just like we did with PyPlot. The type is still NumPy array, 3 channels, nothing new here. And then I'm showing the image with PyPlot again. PIL stands for pillow. Let's see where we imported this. So PIL, pillow, is another way to do this. This is the import statement here, and then the method that we call is called open. We just open the image path. The type is now a pillow object, right? So not a NumPy array, but we can convert it to a NumPy array by simply feeding it into the call np.array, right? So we can convert it to an array if we would like. skimage from scikit-learn. I'm just putting this down here for reference. Import skimage, skimage.io.mread. So you have to go into a subfolder here to get access to the mread method. Notice these methods are all similarly named. The type is again a NumPy array. All right. Something that we'll definitely want to be aware of is that we can read these also directly in with TensorFlow. So under the module.io, we have a method called readFile, feed in the image path. Once we've fed it in, we can decode that JPEG with the method decode JPEG. Notice I'm overwriting the variable name. We can convert it to black and white with RGB to grayscale. I haven't shown this in the other methods up above. I'm showing it for the first time here. We could also convert it to an array. Notice when we print out the type, it's a tensorflow.python.framework.ops.eager_tensor, some kind of TensorFlow object. One thing to note is when we go from color to grayscale, those 3 channels that were either for red, green, blue, or hue, saturation, value, and perhaps a 4th channel for opacity, sometimes called an alpha channel. When we convert from color to grayscale, we no longer need all those channels. So once I've converted it, I can reduce the number of dimensions of my NumPy array that represents the image to 2 dimensions. So instead of having 3 channels at each pixel location, you have 1 value at each pixel location, and you're able to condense the information into a 2-dimensional image. We do that with tf.squeeze, tensorflow.squeeze. All right, exercise here. Find 2 different images on the internet, any 2 of JPG, PNG, and SVG format. These will be the most common formats we read and write to. Load them into Python as a colored image, and then also convert it to grayscale using TensorFlow and PyPlot. So I want you to use those 2 methods. Convert to grayscale using the method we saw above, RGB to grayscale for one of the image is an np.dot for the other. I want you to think about this np.dot statement. We played around with numpy.dot last week, or at least some of us potentially did when we wrote our own function for a perceptron, right? We had the weights that needed to be dotted against the incoming feature vectors. So I want you to think about what weights you would use if you're trying to condense red, green, blue channels into a single intensity channel. Something to keep in mind is each of these channels has 256 unique values. Has to do with the bit, the way we store this information into bits, the default amount of data density we have for these images. So you'll want to think about that. I'll go ahead and walk us through one of these with some images that I found. All I'll do is Squirtle. We can do image equals tf.io.read file, and then the path to file is just going to be that path up there. I already saved my image. And we'll overwrite this variable. All right. And quick note here, sometimes there's an extra channel for opacity like I mentioned above. In my Squirtle case, I believe that's true. It's RGB to grayscale, and this will be image. And I can just automatically go to the first three channels with this, right? So if there is an alpha channel, it just cuts it off. That should work. You can use squeeze, image. These tooltips are kind of annoying sometimes. Let's just run this, see if it works. Cool, and then we can do CMAC equals gray if we want to get rid of the viridis. The default CMAP there is viridis. Don't be fooled. This has the colors removed. Viridis just displays intensity with hue. All right. We'll leave the dot product as an exercise for you all. Moving on to CNNs. CNNs, short for convolutional neural networks, take the gold for machine vision. We'll talk about what convolutional layers are in a moment. For now, let's talk about the general structure of these types of neural networks. A CNN consists of a base and a head. A base and a head. They both are these are layers of the neural network. Go into more detail here in a moment. The base is used to extract the relevant features from the image. It consists mainly of convolutional layers, hence the name. The head is used to map those features to the classification task and mostly consists of dense layers, the kinds of layers we learned about last week. Now, what is a visual feature? It is a relevant abstraction from the image data, often taking the form of edges and shapes that then form more abstract objects like eyes, ears, or wheels and windows. Right, so in the initial layers, we're taking and extracting the lines and edges from the image, and then we're organizing those into higher hierarchical objects like windows, bodies, rims, and tires. This is all taking place in the convolutional layers, and then also known as the base. And then in the head, the dense layers, once we have those objects identified, we can say things like, okay, well, if it's got 2 wheels, it's this thing, or if it's got 4 wheels, it's this thing, right? If it were to like classify cars from motorcycles, for instance. So those are done by the dense layers, the separation out into the classification task. A classification neural network will always have this phenomenon where early in the network, layers are learning features, and later in the network, layers are appropriating those features to different classes. In a CNN, this phenomenon is accentuated by the base head dynamic. Given that the feature generation task can be very similar across images, often we use the base of a pre-trained model. This strategy is called transfer learning and is extraordinarily powerful when dealing with small data sets. So the idea here is that the feature extraction process is going to be similar across many different tasks out there in the world. And so you can take that base of a pre-trained model and apply it to your specific classification task, so that when the images are pumped through it, they get defined in terms of objects or edges or whatever, and then you just put a dense layered head on it that can then map those features into the actual classification task. And this isn't unique to CNNs, it's just that it's accentuated by CNNs because the base and head are so heterogeneous in terms of one another. There's completely different layer types. Other note from I took from Kaggle: when doing transfer learning, it's generally not a good idea to retrain the entire base, at least not without some care. The reason is that the random weights in the head will initially create large gradient updates which propagate back into the base layers and destroy much of the pre-training. Using techniques known as fine-tuning, it's possible to further train the base on new data, but this requires some care to do as well. So when you go and do this in TensorFlow Keras, the hyperparameter flags that you set for training are going to say whether or not you want to freeze certain weights. That just means you don't update them during backprop. And what they're saying here is you'll typically want to freeze weights for a base that's being put onto a new head. Otherwise, the differences between the randomized initial weights in the head and the pre-trained weights in the base can lead to really obstructing or changing those pre-trained weights in the base. So you'll want to give the head a chance to kind of assimilate according to the base before you allow the base to change and update. That's the topic for another course. All right, so this is the fundamental architecture of a CNN. Now we're going to talk about the inner workings of the CNN. Convolutions, rectifying linear unit, and maximum pooling. We'll now discuss the three heavyweights for CNNs: convolutions, RALUs, and max pooling. You can think of these as the agents of three primary steps in a convolutional network. Step 1, filter an image down to features. Step 2, detect that the feature is present. Step 3, condense the image to enhance the features. And this is the three steps: convolution, ReLU, and max pooling. These three steps are demonstrated in the following images. So on the top left, we have our input, looks like the grille of a Bentley. Our CNN or filtration step pulls out the edges and the important gradients, the extreme gradients. Our detection or our ReLU step subtracts out anything that is unimportant, right? And so it just really highlights those gradients. And then the condense or the max pooling phase, it's hard to tell here, but we'll explore it further on in the notebook. What it does is it removes some of the unimportant information. This image is actually reduced down to 25% of the number of pixels in the condensed. Starting with the convolution. The convolutional layer carries out the filtering step. We can create a convolution in Keras like so. So I'm importing Keras from TensorFlow and then layers from Keras within TensorFlow. And just as we've seen in the past, I'm going to access the layers library and pull out the object I'm interested in this case, a convolutional layer. The hyperparameters we're going to be talking and discussing are filters and kernel size. Let's talk about these hyperparameters. The weights a CNN learns are primarily in its kernels, what we've called filters here. And kernels are a collection of arrays that are passed over the image to produce weighted sums. Here's an example of a 3x3 kernel. A weighted sum, that should sound familiar to you. It should sound familiar because this is the same idea as when we applied weighting to scale our RGB to a grayscale image up above further in the notebook, and when we took the dot product when we wrote our own perceptron. It's the same exact idea. So here's an example of a 3x3 kernel. As the kernel is swept over the image, it acts to accentuate certain features. For instance, some kernels will bring out vertical edges, some horizontal edges, others will accentuate gradients in a general sense. So we're showing the input image here in the bottom. So these are just pixels with some kind of intensity value. You apply the kernel over that window on the input image, and you take the dot product of it, right? So you multiply this location by this location by this location, and then you sum all the multiplication to get a final output. As we train our CNN, it learns what kernels are best for learning relevant features for the given classification task. We set the number of kernels with the features, or is it features? It's filters. With the filters hyperparameter, boop, boop, boop. With the filters hyperparameter, and the shape with kernel size. So here's kernel size, 3. So this is short for, I could also do 3, 3. The reason I can put a single number there is because I'm symmetric, but I could also make this kernel arbitrarily different numbers. But if it's symmetric, I just put a single number there, 3 by 3. The shape will usually be an odd number so that the kernel is oriented around some center pixel, but this is not a requirement, right? So we like odd numbers because then it's immediately obvious to us how these output and input arrays align with one another. All right, activations. The activations, also called feature maps, are the output from the kernels. We can see an example. So each of these 3 pink subimages are a feature map that have been created with the above kernel for each of those. We see that this kernel that has a gradient within its own self in the horizontal direction brings out horizontal gradients. This one as well has a horizontal gradient. This kernel has a diagonal gradient. We can see that it picks up some of the vertical as well as diagonal gradients in the Bentley, right? Look at this hood gradient versus this hood gradient. Notice that in general, the left and middle kernels are augmenting horizontal gradients or boundaries. All right, ReLU. The ReLU should be familiar by now, right? We saw it used at the end of our regular dense neural layers. It appears here in CNNs to further isolate the presence of features in the feature maps. Remember that it sets anything below 0 to simply 0. It's the same exact thing as we saw before. And in a way, it is saying anything that is unimportant is equally unimportant. Let's see it in action. So these are the same kernels as above, and I've now gone ahead and moved one step beyond just applying the kernels to now applying both the kernel and the ReLU step. You see that all of that background information was subtracted out of the first 2. We still have some here in the third one because the kernel as it was applied to the original image didn't result in a lot of values that dipped below 0, but it did result in some. Notice down here, although they were 0 to begin with, weren't they? Those black areas in the black and white image. And just as with dense layers, the ReLU allows us to create nonlinear relationships within our network, something that we definitely want. All right. Exercise, experiment with kernels. So I'm just going to load in some of our data that we have ready for today. These are motor impellers. So these are impellers used for maybe pumps, some kind of pump, and these are casted motors, so they're poured into a mold and then taken out. Some of them are going to be defective and some of them are going to be okay. And then what we're going to do tomorrow is train a CNN to be able to classify whether a given motor impeller is defective or not. I'm going to define a kernel. There it is, our nice little kernel. And we're going to prepare our image to apply our kernel, and then apply our kernel to our image and look at the resulting feature map. We can then apply the ReLU step, right? So subtracting out all of the stuff below 0. We're going to wrap these steps into a function and simply play around with the kernel to see how it changes the feature mapping for this impeller. So I've just created some code here, apply the kern that will allow us to quickly iterate over different kernels, applying them to the images. So now, if you want to play with this, you can. I'll just change this so that I'm only defining a gradient in the vertical direction and see how that changes the output. I want us to notice that as it's defined now, I'm getting gradients in all directions, right? I'm able to capture all the circular gradients in this impeller. Now if I apply this kernel that has a gradient going from left to right, I see that I'm really accentuating gradients in the image that appear on the horizontal plane. All right. If you are watching this, be sure to take time to play around with that kernel, establishing different gradients, playing around with when the kernel itself sums to something larger than 1, or 0 rather. All right, condense with maximum pooling. In this last step that we'll cover, we're going to condense the image in a way that accentuates the identified features. Let's see if I can mute this. All right. In this last step that we'll cover, we're going to condense the image in a way that accentuates the identified features. This is done with MaxPool-D layer in Keras. A MaxPool2D layer isn't much different from a Conv2D layer, other than that instead of taking a sum, the kernel, which is not really a kernel, right, just returns the maximum value. The kernel size is replaced with pool size, and there are no trainable weights. That's what makes it not be a kernel. Features are indeed intensified by the max pooling, but another way to think of this is that carrying all those empty black pixels through the network is computationally expensive without adding much information. Max pooling is a quick and dirty way of consolidating the network and retaining only the most salient information. So we're going from the image on the left to the image on the right. And you can see that these white grid spaces represent the max pooling window. So out of this top left square, I want to take the maximum value, and that's associated with this output. Out of the next to the leftmost square, I'm going to take the maximum pixel out of there, and that's associated with this pixel value, and so on. And so we're able, if you look at the center, to go from what was originally 1, 2, 3, 4, 5, 6, 7, 8 times 4, 8, 16, 24, 32 pixels here were consolidated down to 8 pixels, right? So we're removing a lot of useless information without degrading the overall shape of the feature in the original feature map. And we can see an example of it here. And to finish off left as an enrichment, practice with global average pooling. Usually at the end of the convolutional blocks, we use a flatten layer to convert the 2D arrays of feature maps to 1D to feed into the dense layers of the network. Another method that has become popular is to use global average pooling. With this schematic, each feature map is turned into an average. By this method, the head of the CNN now only has to make a classification based on how turned on the feature maps are, indicated by the result of the global average pooling. And we would implement this with Keras like so. So this is something that is definitely worth playing with when you're going to fine-tune a CNN, because you can think of it like if you had feature maps that were specific for, and they learn these on their own, right? You don't dictate this. This is the purpose of supplying relevant examples, right? But each one of these kernels could be in charge of, finding a wheel or finding a window or finding a smile or a frown. And if you do a global average pool at the end of it, you get a single number that tells you how intensely is that feature map appearing. And so this is a pretty solid technique if you're wanting to fine-tune your CNNs, rather than feeding in the raw feature map data into your dense head layers. And that is it.